Hello, everybody. Can you hear me all right? OK, great. Hi, my name is Tintu Pathrose. I'm the manager and lead of an analytic engineering team back in Discover. After me, you will hear about some cutting-edge technology on distributed computing from Nicholas and Sushma. So let's start. So our lawyers made us say this. So we all know how important analytics is these days and the power of AI and the decisions that it can make, right? Every decision has to be backed by the best machine learning models behind them. And that's where the collaboration between H2O and Discover really comes in play. With their very innovative machine learning algorithms and their very easy-to-use APIs, we can make our models much better. But one of the key challenges that we face in our existing environment is these generations of old platform, which doesn't provide that consistent behavior that we want it to be. So it takes months to upgrade a newer version of H2O, so the users have to wait to get that upgraded. So that's when we started looking into building our own next generation analytic platform. So we built one in cloud called AirMine. It's a self-service machine learning platform, very intuitive, with a very intuitive user interface for the end users. So the end users, once they go in, they can provision their own personalized work environments. So we offer choices like H2O, Jupyter, RStudio, SAS, and currently we support 4 versions of H2O. And they can choose any of the version, and they can choose how much compute and RAM they want for their jobs. And once they make all the selections, they can submit the request. And behind the scenes, our provisioner takes it into play, and then the user gets their own personalized environment. Through the UI, they can manage the projects, the iterations that they want to run through, and the personal environment. And once the job is done, they can terminate it or suspend it and can resume it back later. So one of the key advantages of this platform is that they no longer will have to share their resources with anybody, like when you compare with Hadoop environment with a huge resource bucket, and everybody is battling over there. On top of this provisioning, it also provides many other capabilities. Like they can provision dataset from Snowflake, which is our cloud data warehouse, and we can provision this dataset and put it for their container, and they can actually easily access the dataset from there. We recently added in the support for distributed computing, which you will soon hear from Nick. So as I said, it's a very simple UI. People can manage their projects and iterations. But behind the scenes, there are many components that work in play to make this happen. We completely run on Kubernetes, which is our container manager. And we also have many diverse EC2 instances that work behind the scene. So we have high memory nodes and high compute nodes, which helps our provisioning. We also use EFS as our persistent storage layer. So that's one of the advantages of this platform. It has a decoupled storage and compute layer. What that means is we are no longer trying the users to use one particular tool or a version of that tool. They can start a dataset in one ML tool and can move on to a different version or different tool and try out different variations and can make their models much better. We use Postgres to capture all the user activities, so every request can be traced back to a user. And we use S3 for backing up all the data and code, so we can always trace it back from our backup storage. On top of it, we also allow the users to commit their code in GitHub, which can later be productionalized. So this is how the end user sees it. It's so easy for them to choose from the tools that allow ML. And on top of it, they can choose the hardware, as I mentioned, like how much compute and memory they require. We also allow them to collaborate with their team members, yet have enough privacy from other teams through EFS persistent layer. Once they make the choice, we provide them the environment through a web interface and a containerized environment. So it works the same way as it's on my machine than anybody else. But one of the challenges that we ran into was how to make large dataset work in this environment. And that's when we started looking into distributed computing. And to explain about how we did it, let me invite Nicholas Anderson onto stage. Nick. Thank you.
Hello. Hi, my name is Nick Anderson. I'm a data engineer working on this AirMine data science workbench. I'm going to talk a little bit about that, but the main thing I'm talking about is more of a technical deep dive of how we're running distributed H2O clusters on Kubernetes. I'll talk about the how, the why, the interesting parts are the hurdles and the kind of solutions we came up with to get around it. So first, like Tintu mentioned, AirMine is our self-serve data science workbench. We took this whole container-based approach. One, decoupled compute and storage was the main part, but the key advantage of container is there's also isolation between software and hardware. We don't want to configure a whole system for multiple users. We want the users to make their own customizable, flexible environments for them to use, such that user one can try to break, destroy, ruin their container as much as possible, but would never make an impact on anyone else's containers. So from our workbench, you see on the left, there's our 4 tools of choice. But we also give the users option to choose their hardware. For this, we went with a t-shirt size recommendation. So we have size small, medium, large. Our small one is 1 core, 8 gigs of RAM. But this goes up into our biggest size, being 4 extra large, which is 32 cores and about 1/4 terabyte of memory. So the reason behind this is if a user just wants to try out some code syntax, some custom functions, and they, on a small sample of data, they don't need a huge beefy server to do that. A small would suffice. Whereas if a user wants to do a giant grid search on XGBoost on 10 gigs of data, of course, you need a lot more compute power to do that. So we let the users define that. Containers are very stateless. They could bring it up, bring it down, their compute environments. Their storage always persists and remounts. So the idea of bring up environment within seconds, bring it down, and not use it. We allow the flexibility of our users to do that. And lastly, how we kind of give users recommendations for the t-shirt size. Usually things break when your data set's bigger than memory, or your memory is not too much bigger than the data set size. So for especially H2O, we recommend provision an environment where you have at least 4 times more memory than the data set size you're working with. All right, so this is my kitten, Onyx. He's back in Chicago. I took him to a vet recently, and the doctor said he was kind of chunky. So I thought this would be a good slide to represent a huge compute resource request and a relatively small container to fit it in. So the idea is for the majority of the users, our data scientists, analysts we onboarded to AirMine, the size is small to 4XL, worked great. But then we started onboarding some big data users. These users had files in the size of 100 gigs. So of course, 400 gigs of data can't fit into 200 gigs of memory. So we needed a way to scale out this box. So there's 2 ways to scale. You can vertically scale or horizontally scale. Our general purpose nodes we're running these containers on, they are high memory nodes, but like I said, not big enough. Amazon always brings out new high memory instance classes, but there eventually will be a physical limit. So scaling vertically on a single node, pain to manage, super cost. It's like a sore thumb if a big node sticks out, and just constraint. So we want to scale out horizontally, which is kind of more native in 2019, as we can spin up more nodes with scaling. So next, I'll talk about how we scale out a H2O cluster on containers on AWS. So initially, to spin up H2O cluster on bare metal is very straightforward. All you do is pass in an additional parameter called a flat file. The flat file has IPs of all the nodes you expect to be running in the cluster. So if I want to spin up a 3-node cluster on Amazon, I could spin up 3 EC2s. The thing is I need to know the EC2 IPs. That's fine. I create a file on all the EC2s with the 3 IPs and basically launch the Java jar for H2O at once, forms a cluster. So very straightforward, but running this on a Kubernetes platform has 3 kind of big hurdles. First one, when you spin up a pod in Kubernetes, that pod IP is dynamic on creation. You can't run out an elastic IP with AWS and persist the IP. So when I spin up a pod, I don't know its IP until it's created and running. That's the first issue. Second issue is that flat file needs to be on all of the servers or nodes the cluster is expecting to run. Since the IP of the container is not created until it's running, we need a way to basically create a flat file accessible from all the containers such that it knows which pod IPs are expected to be part of the cluster. Like I said, dynamic on creation, so we have to kind of handle that on the fly. And the last issue was, since these are images, even though images, Docker images, they're very lightweight, they still have a base operating system they're pulling from. It's a few hundred megabytes for a RHEL base. So it takes about a minute to pull if the node doesn't cache it. So this would be an issue when, let's say, I wanted a 4-pod cluster, but pods 3 and 4 landed on a new EC2 node that's never pulled the H2O image before. I don't want pods 1 and 2 to spin a cluster without involving pods 3 and 4. Since H2O clusters are very bring up, bring down all at once, they don't have a really good way of attaching after it's formed a cluster. We want to make sure that pods 3 and 4 are part of the cluster, even if it takes about a minute for it to pull or other issues. So that's the third hurdle we have to kind of account for if we want to automate and make sure there's a robust way to bring up a H2O cluster on pods. So here's a quick, maybe 2 minutes less, the solution for these 3 things. They're kind of custom ad hoc solutions. They're kind of figure out a way to do this. But the first part, the pod IP, so this one was really easy. Kubernetes offers metadata about the deployment. So you can pass in the pod IP as an environmental variable from your deployment config. So when the pod creates, the pod has its own IP as an environmental variable. You can echo it out, write it out. So that's done. Second part, this is kind of a really cool part that's enabled by AWS. You need a shared storage space such that all these pods can read and write to, and only the IPs that are expected of that cluster. We don't want one giant location where all these different clusters are writing to, because H2O needs to know exactly which IPs are to be expected in that cluster. So for this, we're using Amazon's EFS. That's the Elastic File System. And one really cool part about this is it uses the NFS protocol. This allows the storage not to be mounted to a single host, but tens, hundreds, or thousands at the same time, and it's the same physical storage. Because of this, when we spin up a cluster, we create what's called a PVC. It's a persistent volume claim. This is a unique volume claim just for a single cluster. And this volume claim gets mounted to all the pods that are part of that cluster. So now we have some shared space that all the pods can read write to, and only those pods have access to that. And then lastly, the whole issue with the node image cache delay. So this one wasn't too bad. We basically create our own H2O image, and we modify the entry point. So this entry point, it knows the number of replicas it expects in its cluster, which is basically how many nodes are in a cluster. And then it's constantly scanning that flat file. So if I want a 4-pod cluster, I expect 4 unique pod IPs to be in that space. Each of those containers will not kick off the H2O jar until it knows all 4 IPs are ready and are in that flat file. So it's kind of a poor man's way of waiting, like, hey, is everyone ready? All right, let's go. So that's how we handle the 3 problems. And because of this, we have a single deployment config, and we just choose number of replicas, and then we can spin up an NX-size cluster such that the collected resources is always greater than a single node. So that's kind of how we handled kind of vanilla H2O clusters on Kubernetes. So what's really good about this, we don't need super high memory EC2s. This runs on our general purpose high memory nodes. And since we have auto-scaling groups in place, let's say I wanted a crazy 200-pod cluster, and I only have 10 EC2s running in my cluster. We have auto-scaling enabled. So when Kubernetes makes that API request saying, I need these resources, Amazon will spin up those EC2s. And because of the intelligent entry point, it will wait till those EC2s are ready, pull the images, and deploy it once. So it's kind of a robust way to scale up, scale down for these kind of big bursty clusters. And then users can always connect to it from Jupyter RStudio, just using a pod IP. And of course, we have like LDAP credentials authentication. So that was a quick tech deep dive of how we incorporate distributed H2O containers with our environment that sits among our Jupyter pods, our RStudio pods, our SaaS pods, and how we can handle big data users as well as our normal data scientists day to day. So next, I'll pass it off to Sushma. She's going to talk about how we run Spark and Sparklingwater in a very similar way. This is for users who do ETL, data munging, and then model training on top of it in the same context. So I'll pass off to Sushma to talk about that.
Yeah, I'm Sushma Manjunath. I work as a senior principal at Discover in the same group as Tintu and Nick. Transitioning from H2O distributed, we wanted an integrated single platform to run data cleansing, munching, and all the goodies of machine learning and H2O in one place without having to move data back to storage, back and forth. And when we first started with Spark in our version 1, we built images for Spark masters, slaves, stored them in a Docker repository, and just spawned clusters with those. For best user experience, we did all of this dynamically, taking user requirements for cluster sizes, CPU, memory on demand as the user requested. Spark slaves were just replicas of the same image, where we set the master to the master in the pod, and we bring up Spark in this fashion. It works in a standalone mode. Standalone will work fine for simple, easy non-production workloads. One of its limitations, of course, is that it runs with a FIFO scheduler. So jobs can get queued up and wait for them to run. And another problem is all the jobs submitted to the cluster will all run with the same cluster configurations. This, along with the fact that we had to manage multiple clusters for multiple users and have to address log aggregation issues, we decided it's time to try something different. And our second option, at this time, Spark had come out with Kubernetes natively available Spark. And Spark 2.4 was better integrated, and it was also available in client mode. So that fit perfectly for us into our model, like Nick and Tintu already spoke about. We had a Jupyter pod that users interacted with, and all the Spark jobs were submitted from there. So the idea was use Jupyter and submit the driver from there and use client mode for it. When we see in the PowerPoint here, we see the driver and executors, and it appears like the driver is spawning all the executors. But in reality, the driver only speaks to the Kubernetes control plane, and the control plane schedules the executors to run on the cluster. So the driver doesn't really need to talk to anyone else other than Kubernetes, and the executors are the ones that need to reach back to the driver through the network connections. We tried this with Sparklingwater. We ran into a snag. Sparklingwater built its cluster flat file with all the host names for the driver and the executors. But the host names are not really available in a Kubernetes cluster, and we needed them to be IPs. Working with Kuba and the Sparklingwater team at H2O, they were quickly able to resolve it and give us a patch to fix the IPs in client mode. And once the cloud came up, we were back in business, and Sparklingwater clusters formed just fine. We used both Kubernetes. From Kubernetes, we used the EFS mounts and the S3 buckets to deliver data to the executors. We pointed our Spark logs over to another EFS mount, and we spun up a Spark history server in another Kubernetes pod to read those logs. This gave our users accessibility to our application logs, which made everything more visible and usable. Now, going to the next slide. What worked for us with Spark and what didn't work with Spark was the first thing, the Spark submit syntax was very easy to use for our users. They were already familiar with Spark submit on other platforms, and we were able to abstract a lot of the configs. So it was very easy to use for them. The option, since Kubernetes, Spark is using the Kubernetes resource manager and the control plane, we just decided to try if autoscaling would work. What we saw was the latency to spawn the nodes using autoscaler in our environment was too slow. it took about 40% of the latency time to just read the images from our repository. So this wasn't acceptable. We're still working with our internal partners to see how to address that. Another issue is that dynamic allocation and external shuffle service features are not really available with Spark Native. This can be a huge hindrance if you're going to do ETL workloads and try to use production SLAs in Kubernetes. That can be a showstopper for you. One more concern we had in our environment was a lack of support for user-defined driver and executor templates. What I mean is we weren't able to customize the driver and executor templates to suit a particular user. So we weren't able to mount the user's home into the executor in any fashion. So that makes it, if you're a highly secure environment, it can be a concern. Since you want your service to be only able to read particular data and not all of your data. As far as application management, the application management wasn't exactly where we wanted to be. There is no console access to list all your Spark jobs, kill Spark jobs, and things like that. So there's a lot to be desired there as well. Spark Operator, we tried the Spark Operator in our Kubernetes environment, but the Spark Operator uses APIs that are really not compatible with our Kubernetes versions. So we're working on that as well with other internal teams to upgrade the Kubernetes cluster. So more to come there. With all these limitations, we decided that it's best to just roll out Spark and Sparklingwater in a limited fashion to experiment with and play for machine learning. We're still not in production yet, but we hope to work with H2O as we upgrade to Spark Operator and take us further on our Spark journey. I would like to invite Tintu and Nick for closing comments and questions.
So we have a large user community, H2O user community back in Discover. And because of this containerized application, we can now broadcast newer versions much faster than we did before. And the users can try out these versions and let us know how it really helped them. The next in line, we are also looking at validating these models in coming releases. So we hope to continue our great partnership with H2O. And with that, we will take questions.
Thank you. Thank you.
Thank you.
No questions. Yay.
You guys
I got a question over there.
Can you hear me? Okay. How does H2O make a difference in this use case versus you were to use XGBoost on Kubernetes?
So we're the data scientists. We're providing infrastructure. And our data scientists have been working with H2O on-premise for a long time. So code syntax-wise, they're used to H2O for XGBoost, GBM. That's what we notice. So H2O, there's a lot of different distributed options for these kind of algorithms. But H2O is what they use natively, even non-distributed mode. So for them, they almost don't know it's a cluster. They just see the collective resources on more. So it's just more code syntax and what they're used to. And spinning up H2O is very easy. So this is kind of our first test case of distributed mode.
I think that's it. Thank you, guys.
There's one more.
No, there's one more. There was one right here. There's a couple more.
Okay.
Yeah, throw it.
We have a question right here.
Hi. So the first part that you're talking about is more towards installing H2O on EC2 instance, right? So I'm assuming you are installing a native H2O component on top of EC2 instance, correct? So as that means my follow-up question for that is more like how you are communicating or how exactly you're distributing the model when you're managing your own H2O instance.
Sure. So for us, we're not installing anything on EC2s itself. We're running everything as containers. So basically, it's virtualized, isolated packages with H2O jars on it. So we're not moving anything to the host itself, just deploying a container in there. For the actual networking, between our nodes, we have all TCP, UDP. For us, H2O listens on 54321, and that's what we pass in a flat file. So node-to-node networking in terms of security groups is already in place. And Jupyter Hub's in the same sub-network of Kubernetes, so all the networking is already in place. We don't have to do any additional configurations because it's all internal traffic. That answers your question.